So the second enabling technology for our next generation GPU is 3D packaging. We're going to, for the first time, build chips on top of other chips. And we're going to pile heterogeneous chips, meaning different types of chips, on one wafer. It starts out with a base wafer, where interconnections are being done among the chips. So instead of going off to a PC board, we're doing the inter-chip routing on the wafer. Thousands of little bumps characterized by that vertical signal on these chips are flipped and bumped onto the base wafer. We're putting so many bits. In fact, the memory interface went from hundreds of bits to thousands of bits. Thousands of bits. If you could just imagine a GPU with thousands and thousands of memory interface bits. The question is, how do you put those bits on our chip? And how do you connect them to all of the memory? Well, the way to solve that problem is we stack all of the memory chips one on top of each other. And we punch holes through the memory using through-silicon vias. And each chip, each DRAM, is then stacked on top of each other. The stacked DRAM, which is 3D memory, is stacked on top of a wafer. That wafer, because it's a silicon substrate, can now have wires incredibly, incredibly small that connects it to our GPU. And together, it forms an interface that delivers an unbelievable amount of bandwidth, a huge leap. And so if you take a look at that chart, the solid green line is where we came from. And as you can tell, we've been trying to deal with the memory bandwidth problem for some time. Although we are already the highest bandwidth processor in the system, there's so much more bandwidth we wish we had. And if we want to continue to scale with Moore's Law, we're going to have to solve this problem. Well, 3D memory and 3D packaging using the heterogeneous 3D chip on wafer integration makes it possible for us to take a giant leap forward. The green dotted lines gives you a sense of where we're headed. In just a couple of years, we're going to take bandwidth to a whole new level. And so the question is, what are we going to call this chip? This is one of the great chips, one of the great GPUs we've ever made. And it incorporates, in addition to architectural innovations that we'll reveal to you over time, incorporates these two enabling technologies. First time we've ever used it as a company. We're testing it rigorously now, and we're excited about the results. What should we call this chip? Well, we should certainly call this chip and name it after somebody, name it after a scientist that we all recognize and admire. And Blaise Pascal is really the perfect name. Blaise Pascal, a Frenchman in the 17th century, at the age of 16, invented the mechanical calculator. He's responsible for probabilistic theory to help a friend who apparently had a gambling problem. He's the man behind the Pascal's theorem, where intersecting lines from points on an iconic all lie on what is called the Pascal line. The Pascal's theorem is foundational to many of the works that we do in projective geometry. Pascal's law of hydrodynamics is applied to hydraulic lifts, hydraulic brakes. We're surrounded by his work. The unit of pressure is named after Pascal, and a program language is named after Pascal. It is very appropriate for us to introduce to you our next generation GPU, Pascal. Pascal is really amazing on several levels. Let me show you. This is the Pascal computer. This little module here represents the processor of next generation supercomputers, next generation workstations, next generation gaming PCs, next generation cloud supercomputers. It's based on a technology called NVLink, uses 3D memory to amplify the bandwidth between GPU and memory subsystem, and it fits in a module that is a third the size of PCI Express. This little tiny module is elegant, it's just really, really beautiful. This is the test module for Pascal. And so what's Pascal going to do? Well, here we're showing you some of the results. This is SGEM simulation. Comparing to our previous generation GPUs at constant power, ISO power, comparing generations of our GPU. As you can see, because of NVLink, because of 3D memory, because of the architectural innovations of Pascal, we can now continue to scale with Moore's Law. A scale that most people feel that will eventually fall off of, but it's not going to happen with Pascal. We're going to continue to scale performance. In fact, I'll even predict that in multi-GPU environments and in large configurations, Pascal will do even better than previous generations. And the reason for that is NVLink. Now the question then is, what are we going to do with all this computational horsepower? What are we going to do with all these flops? What are we going to do with a processor that's essentially a supercomputer the size no bigger than 2 credit cards?